Okay, we're going to go through one of the most useless chapters in the book because you can't do the derivatives for a lot of them by hand. They're just too complicated. It's optimization problems. So mostly for optimization problems, what you're looking at is a peak of a curve to find where you maximize something. Could be profits, could be something growing like bacteria, or anything. But regardless, this section has so many derivatives that you can't do. It pretty much makes you go to the computer that it's kind of useless. So just understanding it is important. So I would say just understand the basics, which is the derivative of e to the x is e to the x. It's the same result. The derivative of 5e to the x is 5e to the x. And really the only complicated thing would be something like this. The derivative of 5e to the 5x, or let's call it 6x, is 5e, 5 times e to the 6x, times the derivative up here, which is 6, which can then be simplified to 30 e to the 6x. The other thing I'd want to caution is when you solve these things, sometimes, for instance, you want to see that when will this 6 to the 6x equal to, let's say not 0, but let's say 100. Let's say it says, this grows to 100 population of whatever. When you solve it, the only way to solve it is to take a ln or a log. In this case, a ln is a log to the base e of both sides. But the problem is a lot of people here will make a big mistake, and they'll say, okay, well, that 30 is a multiplier, so it can just come out here. And that's not the case. What we have is, here's a ln of both things, which means we have a product rule. So you then would have to say, okay, ln of 100 on the left is equal to ln of 30 plus ln of the e to the 6x. We would have to subtract that ln 30 so that we can isolate this. So we would get ln 100 minus ln of 30 on this side is equal to ln of e to the 6x. And it's at this stage and only this stage that the rules of logs let us bring down that exponent in front. And of course that leaves ln of e, and since ln is the natural log of anything, the ln of e is just 1. Anytime you have a log or ln where the base matches the number, the answer is just 1. So that gets rid of this entire thing. And so now you just divide both sides by 6. And there's your answer. Now you could also divide each of them independently and get rid of this part here. Now they're their own two separate fractions if for some reason you wanted to do that. However, I see a lot of people just putting the 30 up front. Don't do that. I'm going to go to this chapter, and I have to say we're not going to spend a lot of time on these questions. They even introduce the idea to you in the very first one that you should be going to a graphics tool a lot of the time. When they show you this example, and they ask you which was easier, using the graphics tool or finding the extreme values using the derivative. It does help you to analyze some of these things. And it also helps you to analyze, understand functions or basic graphs. Normally e to the x would be a growth curve, but e to the minus x is the same as 1 over e to the x, which pretty much produces a decay curve. Another way to look at it is this growth curve here would look like that, but this minus reflects it in the y-axis, and therefore looks like this. So all the x values would go over here and change their sign, and all the x values over here would go over here and change their sign. That's all that minus means, but it essentially turns a growth curve into a decay curve. So while this is a growth curve, this becomes a decay curve, and even when you write it like that, it becomes obvious why this thing gets big. As a result, the whole fraction gets small. When this thing is small, the whole fraction becomes big. essentially just turns it into a decay curve, which makes you ask, why are we using E in the first place? Here we have one smaller decay curve subtracting a compressed decay curve, which means this curve will look like something like this. And this other curve will look something, this one will look something like this. Much sharper. But there will be a moment here when the minus will actually produce a positive value. And over here it won't. So your resulting graph, because over here the blue graph is very powerful compared to the red graph, it's way up higher in values. So the result with this will be negative, except for the small areas here. So what you'll see is when their x is 0, for instance, it goes through 0, 0. And the graph will look something like this. It'll have a nice little bump here while this red line is much bigger than the blue line, not even that much bigger. And then it'll come down as they become pretty much the same. And they will try to approach but never reach 0. And you can see that when you put an extreme value on either of them, 1 over infinity here, minus 1 over infinity cubed, essentially, will, or rather, e to the infinity, and 1 over e to the 3 times infinity, will still result in almost 0, minus almost 0, and it'll never quite reach 0. And if anything, this fraction will be smaller than that fraction because of that 3 times exponent. So this number here, this result here, will always be smaller than that. Thus, it'll always be above the y-axis and not reach y. So it just helps to understand. That means we're searching for a little bump here. Now, fortunately, this function here is a very easy one to derive, and that's mostly because it is got a plus between them. When it's a product, it's a lot harder to take the derivative. However, the derivative of this is quite easy. The minus comes in front, and then it's just this. And that's because the derivative of this is just this times the derivative of that. The derivative of that is just minus 1. Same with this one. This minus 3 is the derivative of this, so it comes in front and multiplies this minus and becomes plus 3. And then it multiplies the original function. Boom, you're done. Now when you set that to 0, when you set that equal to 0, you discover, when you bring this to the other side by adding it, that it's going to occur when e to the negative 3 over x is equal to e to the minus x. Now you can either ln both sides now or ln both sides later. Let's ln both sides now. This here, again, don't be confused, is the product rule. It becomes ln ln 3 plus ln of e to the negative 3x. This other side becomes ln e to the negative x. You can now use the exponent rule to get rid of those exponents and simply bring it up front. Just move this aside. The rule of logs lets us bring this in front, and the rule of logs here lets us bring this in front. You want to get all your x's on the same side, so we'll bring this 3x to the other side by, oh, it's not plus minus 3x, it's minus 3x. And we'll now bring it to this side and change it to plus by adding it. Now you'll see that they both have an x in common. So you're going to take, I guess, the negative x. Yeah, let's take a negative x out of it. And you're going to be left with ln e, which, by the way, is 1, plus, or it becomes a minus, 3 ln e, which, by the way, is 1. So you're left with that. And actually, I could have converted the ln e's sooner. Like, if I just do it like that, it's more obvious. And 1 minus 3 is minus 2. And so now I have minus 2x is equal to ln 3. And when I divide by minus 2 on both sides, I will get my x value. Now I can tell you that I probably did a minus wrong in there because I'm quite sure it's going to go through 0, 0, and the x value is going to be positive. However, I see that I get a negative. So I'm going to try this again. I have to take the derivative of that. It becomes this, minus e to the minus x. This becomes plus 3 to the e to the minus 3x. When I take a ln of both of them, or sorry, now that I have it, I set it to 0. I take a ln of both of them. So this is a minus. That's what I forgot. And I get a ln. Yeah, actually, yeah, there we go. That's what it did it right there. If I take a minus 1 out of both of them, I get e, because that minus 1 is now multiplying that e. I get e to the negative x minus 3 e to the negative 3x, and that was my main problem, is equal to 0. I can divide it by negative 1. Now if I put this, oh actually no, it wasn't a problem. Let's just leave it like that. And so my solution was to add the minus ex on both sides. And what I think I forgot was the negative up here. Now I can take ln of both sides, so the left side is ln 3 plus ln of e to the negative 3x is equal to ln e to the negative x. So there's my problem. I think I forgot that negative. And it's all equal to 0. Well, no, now it's equal to that. So I can now bring my minus 3x in front, and I get minus 3x times ln e, and we know ln e is just 1. So this here becomes minus 3x. The same happens to the left side, right side. The minus x comes in front times ln e, which just becomes minus x. I'm going to get the x to this side now. There was my problem. I think I had minus 3x before. If I take an x out of it, I get minus 1 plus 3. There's my problem. I had minus 2 before, so it's actually plus 2. X is equal to ln 3. Therefore, x is equal to ln 3 over 2, and that will give me my x value of the max or the min. And there's my x value. At this point, it would help to just have the function punched in. Now, how did I figure out that I had an error so fast? Because I already knew from the graphs that the point that they will share when I subtract them will be when they go through 1. And they both go through 1 when x is 0. So when x is 0 here, I get e to the 1 minus 1, which is 0, which means they go through 0, 0. Since I know the subtraction here is going to be really negative, I know that 0, 0 is the point that it crosses, comes down. That means the max will be positive. That's how I spotted it. But I also knew that this one would have a moment where it's slightly above this one, simply from my knowledge of the function itself. And I'll graph it for you. But now we have to figure out what is the y value when x is 0.5. So I have to take e to the negative this minus e to the negative 3 times the same thing. Very easy to make a mistake. So I'm going to just put my main value I'm going to keep it like this, and I'm going to add it to my memory. I'm actually going to make it negative, so it's going to be easier for me. And then I'm going to clear. And I'm going to go do e to the exponent of that memory. And you can use brackets. Minus e, and here's the difficult part. It's the exponent, you have to open the brackets here, of 3 times that memory, close the bracket, equals. And I believe that's not correct. So I'm going to try that again. So e to the exponent of this memory is what I want. So get 0.57777735. Okay. And I'm going to have to subtract e to the exponent of open brackets, and it's not minus 3 because I already changed the sign in the memory. Close brackets. That equals. It's saying that's it. Okay. Therefore, the y value for this first one is equal to that. Now, and you could figure out whether that's your max or min, but I already know to the left of it, when x is 0, y is 0, which tells me it's going up on the left. Well, if it's going up on the left, then this point I found is a max. You could also take the slope just to the left, and you could remember that I think we had x is equal to ln 3 was the solution. You could take your original derivative. Instead of setting it to 0, you could just put in a value of x of 0 to see if the slope on the left is positive or negative. If it's positive on the left, you know you're dealing with a max. That's old school. You don't want to take a second derivative. That's just painful. Let's look at this next one. This next one's more complicated because you have a line multiplying what is essentially what I've just explained before, a decay curve. So you have this line, and it goes through -2 on the x-axis. Goes through this point right here, which means when it multiplies this result, it will become 0 as well. So that means it'll share a point with the graph. It'll share a point with the graph like that. Now, it also means that this side of the line is negative, and this side here is always positive. Growth curve is always positive. It never reaches the y-axis, which means the resulting curve, which I'll draw in blue, will be negative, like that. Now, since the decay curve is way up here, it's going to be almost a sharp, straight cliff upwards. And then, once it hits positive, this graph is coming down. But for this little while here, the line should be quite powerful compared to the graph. But then as this graph gets closer to 0, it will reduce the value of this again. So I believe we're either going to see something like that or something like that. And you should also see what happens when we hit infinity here. Well, this becomes a ridiculously small number times a ridiculously big number. But let's get the fractions right. It's 2 times infinity over here, and here it's just infinity. So you can see that e to the exponent of infinity will be much bigger than that. So we're going to come, I believe, close to 0. So that means to me we're going to have something similar. Now let's work on just the derivative. Clean it up a bit. Notice they only give us from -4 to 4 as the domain. Domains are sometimes important. You should always read the graph. Anyway, I did that just to see some important points. Another important point is when x is 0 here, this will be 1, but this will be 2, which means it goes through the point 0, 2. So not only does it go through -2, 0, it goes through 0, 2, which tells me between -2x and 0x is the climb from the x-axis to the y-axis, which tells me the peak, oh, you know what? It might be climbing up first, and then it might be doing this, and then coming down through that number. So So the peak might be right there. That would make a lot of sense because this part of the line compared to this part of the growth curve is much more powerful. So the peak might happen before. Let's take the derivative of this. Well, the problem with this is we have the product rule. We have to take the derivative of this times this plus the derivative of this times that. So you can see that in this case, using the actual graph would be probably more useful. So what's the derivative of this? It's just 1. What's the derivative of this? It's the same function times the derivative of up here. So it becomes minus. So we got e to the minus 2x times that. I'm going to leave the x plus 2 alone. Just be aware that this whole thing is multiplying that, right? But we don't need it. I can see an e minus 2x in common with both. So I'm going to factor out an e to the minus 2x. And I get 1 minus 2 times x plus 2. So essentially I've factored out this from both of them. This becomes a 1 when I divide it by that. And this becomes a minus 2. I don't have to divide this because they're multiplying. Just have to divide one of them. And I'm left with this. When I expand that, I get minus 2x minus 4. So I get to the e to the minus 2x, open brackets, 1 minus 2x minus 4, which is minus 3 minus 2x. Now I can set that equal to 0. And the good news is this will never be 0. It's a decay curve essentially that never reaches 0. So that's out of the picture. So when does this equal 0? Okay. So clearly when x is minus 3 over 2, which is also minus 1.5, that tells me, as I might have suspected, the peak of this graph does indeed happen on this side, and then it comes down. It means it goes through 0, minus 2 comes 0 here, peaks at negative 1.5 here, and then comes down, what was it still? Comes down through 0, comma 2 here, which means this value of y is going to be above 2, because this is a peak. All right. Now all I have to do is plug it back into the original equation to figure out the y. Here's the original equation. When x is minus 1.5 in here, I get 0.5. E minus 2, what's minus 2 times negative 1.5? It's plus 3. So I just get e to the 3 times 0.5. Seems huge. Okay, e to the exponent of 3. Okay, it's not too bad. There we go. This is my y value. So for this one, we're going to get x is equal to negative 1.5, and y is equal to this. Let's see if we were right. So the first one, y, or f of x, is equal to e to the power of negative x minus e to the power of negative 3x. Is that one? Nope. There we go. Its peak is indeed where we thought it would be. Yeah, got it exactly. They rounded up to 8.5, but it keeps going. Also keep in mind that this graph was really only looking from 0 to 10, so this point onwards to this point. So if you were going to graph it properly, it would look like that. And this other graph, here's that line I was talking about. And yeah, sure enough, the line takes over. I'm going to just draw the line in there. The line is more powerful than the actual E curve. From this point on, the multipliers, because the E curve is so high and the line has a positive value, the multiplication is this part here until the E curve hits 1. Then the line and the combined curve meet because the E curve is 1. And that's why the combined curve and the line meet at those 2 points, because over here the E curve is monstrous, but the line is 0, so the result will be 0. Over here the E curve is 1, and the line is 2, so the result will be 2. That's why the combined curve meets the line in those 2 spots. Then from this point on, the combined curve is blue. You can see that the purple curve gets so small compared to the line that it essentially destroys the line and takes over. The blue curve becomes the purple curve. For pretty much, if you zoom in, the blue will always be slightly above the purple. That's because multiplying by the positive line above will always raise the combined graph. Now let's find the derivative. Oh, actually we don't have to. It's right there. Did we get it? We did indeed get it. And again, they rounded up, but that's okay. And also, again, keep in mind that this curve had a domain limitation. I think it was -4, smaller equal to x, smaller equal to 4. So the curve itself just looked like that. And the bottom part goes way down. Might have even been 2, I can't remember. So there you go. That's the part they're concerned about. You can see that doing the graph of the second one was much faster than the first one. The first one is easy simply because that negative, this is easier to derive than a product derivation. Okay, a lot of these questions are absolutely useless, so I'm going to skip them. Squirrel population. It just looks like a tough derivation. The second derivative is very tough, but the first is not. However, you would just graph it. You know, if given the option to graph or calculate, graph. The squirrel population, and it is in hundreds, so every 1 unit gets 100. And time, so we're only concerned about time of 0 onwards. So that's a domain restriction you should always be aware of. And if you look at it, let's find out what happens at time 0. At time 0, this thing becomes 0, so e to the 0 becomes 1. 1 times 3 plus 1 is 4, so we get 20 over 4. So that means at time 0, the population is 20 divided by 4, 500 squirrels, because we're dealing in hundreds of squirrels. So that's the initial. However, on the graph, it's just going to look like that. So at time 0, we got 500 squirrels. What happens as time marches on? What happens as time marches on? Oop. Yeah, I'll just put the function out again. As time marches on, and we hit eternity, let's put eternity up there like infinity. You get minus infinity, so e to the minus infinity is actually 1 over e to the minus infinity, which becomes a ridiculously small number. Even 3, when we put that in, becomes ridiculously small, which means we get 20 plus over 1 plus a tiny number. So we essentially get a little less than 20, because that's going to be something. Won't ever reach 0, but it'll become close. So that means the max this curve is ever going to hit is 20. I also feel like it's probably not going to have a max point. It's probably going to be like that, just because 1 over a growth curve is still just a growth curve. These numbers might affect some wiggles, but I don't think there's ever going to be like a turning point on a growth curve like that, because it's just one single part of the curve. The rest are numbers. Determine the population at the start. We did. It's 500. The largest population can sustain is the time can go on forever. Determine the limit. We've determined that. It's 20. Determine the point of inflection. That requires a second derivative, and in this case, it is ridiculously long. And that's because the first derivative will include a minus 0.02 in front. So essentially we got over here, this part of it, when you derive it, that becomes 0. The second derivative becomes 3 times minus 0.02, so it becomes minus. Up top becomes pretty much, you pretty much have to separate it. And actually it's easier if you look at it this way. Because of this right here, this visually will make it easy to understand. This is the same as that. And this will produce a chain rule where it goes in front and it will affect the 20, and then it'll just take that entire thing and make it minus 2. So it'll essentially bring it back here but squared. And then you have to take the derivative of the internal, which becomes minus 0.02 times 60 times the derivative itself. So you're going to have an e up here and an e down here. So the second derivative to find the point of inflection is going to be a ridiculously complicated quotient function, which will drive you nuts. So we're not doing that. And I'll show you how complicated it gets through Symbol Lab. And I'm just going to let it be x because second derivatives get complicated as you do them. So I'm going to take this whole thing, put in Symbol Lab, and I'm going to say derive, and I'm going to show you why you should not waste too much time on certain problems. So the first step, it's saying, okay, well, derive this. The second step is, like we did, we brought it up like a chain rule. The 20 can go outside because it's just a multiplier. You can just take the derivative of the internal. The derivative of this is 0. The derivative of the second part, as I said, it puts the main function down below squared, and then you've got to take the derivative of the internal. The derivative of the internal, they show right here, is minus 0.6e times minus 0.02. So you get this, and then you just have to multiply this minus 0.06 times the 20. So it's going to become negative 1.2. And there it is there. They also have canceled out. Have they canceled out any e's to the minus 2? No, they can't because it's 1 plus down below. And this becomes your first derivative. Then when you take the second derivative of that, because there's an e function up top and an e function down below, you have to do the quotient rule. Notice how the function looks pretty much like a flat line. Also notice our squirrel population. If I put it from 0, x is bigger or equal to 0, which is what they've said. There's no max. Now I'm going to set y is equal to 20, and we're going to make it green. So you can see the squirrel population is trying to reach 20 and never gets there as eternity goes on. But there's also no max. There does appear to be a point of inflection here. Points of inflection are when the curve is accelerating upwards and then changes directions and starts altering directions. My example of it is a ski slope. When you go down a ski slope at first, it gets really, really steep. And at some point about here, it starts getting really, really shallow again. That's a change in direction of the slope. In other words, the slope goes from changing in a negative direction to changing in a positive direction. The second derivative is negative over here and positive over here, and that point there, the second derivative is 0. But you need the second derivative to figure it out. So we're going to derive it. Look how complicated the second derivative becomes. It says use the quotient rule right there. So you get the derivative of the first one times the actual function of the second, which is now squared. So you got to use a chain rule for that. And it goes on and on. So first they take the derivative of this first one to show you that it's just pretty much the same function again. But then they show you the derivative of the second one is the chain rule. And it becomes endlessly complicated. There's lots of cancellations, and even when they solve it, you can see how hard it becomes to figure out the cancellations. It becomes ridiculously hard. But they do indeed cancel out the bottom. It used to be 4 at the bottom, now it's 3, so they got rid of some of it. And when you set it to 0, because this is the second derivative, and the second derivative equal to 0 will be the inflection point, you'd realize that the denominators in these things pretty much are pointless because they multiply over here and become 0. Then you realize, okay, well, this curve here will never become 0, so this part here is useless. And you just have to figure out when is this going to be equal to 0. And that's just using your basic algebra. First we put the minus, the 0.06 over here, now it's minus. Then to figure this out, we have to take a ln, but be careful. This is a product rule here. So you have to take the ln of the negative 0.02. Now, that's not possible. So you can't take lns of negative numbers. So instead of moving the 06 to the other side, let's move the e to the other side and make it positive. Again, we're going to have a problem here. So you could take a minus 1 out of this left side and make it positive. However, you're going to have a problem. So I believe I believe finding the solution to this, either you can't cancel out some of it to set to 0, because there's no such thing as a ln of a negative number. You end up getting invalid solutions. So I believe the cancellations, even though it simplifies it, might have caused us some problems by creating some negative values that we don't necessarily need. Let's try siphoning out a negative from this and put a negative 1.1 here so that this becomes positive and this becomes negative. There we go. Now I can set it to 0.02e to the 0 point. I can make this whole thing equal to 0. And that means this part, when I get the 6 to the other side, is equal to positive this. That might work. Just because you can't have lns of negative numbers. Then it's easier for me to get rid of this multiplier than to take a complicated ln. This becomes 3. Now I can take lns of both sides. This left side simply becomes 0.2x times ln of e. Ln of e is 1. Is equal to ln 3, which means x is simply ln 3 divided by this multiplier. And you can see why I'm not doing it the long way. So you get this value, which means when x is this, or when time is that, you'll see an inflection point. Now I might have done a calculation error because that seems quite big. And rounding up, it's just that. But that should be the inflection point. Now I don't know what the y value is. You would plug it in up here into the main equation. I'm not going to bother. I'm going to let my graph do it and see if I was right. So I'm going to find the point of 54.93, was it? Comma f of 54.93. And according to it, that's the inflection. It actually does look like the inflection point. I'm going to get rid of that just to see it a bit better, and I'm going to do this to see it a bit better as well. Oh. There, that gives me a better view of it. Yep, that does look at the inflection point, and it happens at a nice even 10. So the squirrel population at the inflection point is 1,000, because it's 10 times 0. And we did indeed know that, and we did get our limit. But taking second derivatives of quotient functions with e is a point, and it's just not worth it. What explained the meaning of the graph? Okay, the squirrel population was accelerating. It was increasing exponentially. At the inflection point, it starts decelerating. So that means the slope here was getting more and more and more positive, and here it's getting less and less positive. Exactly as a car would speed up, and at this point the car is still getting faster, but not at as the acceleration is going down. The acceleration of the population is increasing here till there, and then it starts slowing down. You'd sort of call it a sustainability point, where the forest can no longer feed as many squirrels, so they're not giving there's not as many births. The birth rate of the squirrels is much higher here, and here the number of offspring is smaller. That's another way to explain it. I think I did okay on that. The net monthly profit is given by this insanely complex thing. Thank you. And at some points, you know, even when you see that they're reversing the growth, it is a growth curve, and when they keep turning into a decay curve, you start saying, why wouldn't you just use a decay curve? And you're right. You would. You would not use an E as a decay curve for, I mean, it's a natural log for finance. It makes a lot of sense, but at the same time, it's just not worth that precision. Okay, you got a number times a 1 plus a multiplying of a line. So again, this line will go through 1 comma 0. So all the conjoining curve will be negative at that point. Then it's going to pop up and go down just like our other curve. And then it's got 1 added to it times that. So it's actually got plus 10, or let's see, what is that? A million? Yeah. Plus a million added to it. So if this comes out as 0, when this whole thing comes out as 0, this will be 10 million. But let's see what happens when x is 0. This becomes 1. This becomes minus 1. This becomes 0. So it goes through 0, comma 0. I'm going to make sure again, when x is 0, this becomes 0. So this becomes 1. This becomes minus 1. So minus 1 times 1 is still minus 1. And then 1 minus 1 becomes 0. So it goes through 0, 0. So it's interesting that it goes through 0, 0, because the line goes through, oh yes, because we're adding 1. Even though the line goes through 1, 1, the graph won't become positive there. It'll actually become positive 1 over because we're adding 1 to it. Okay, that makes sense. So the line doesn't have as much of an influence because of this 1 added to it. I hope that's not even needed to follow. Where x is the number of items sold, determine the number of items that yield the maximum profit at full capacity, so you can only have 2,000 items. And I'm going to guess at 500 items, the max capacity is going to be 500. Because I'm going to guess that this curve is going to go like this and max out way over here at like 1,500, which means over here at 500, that'll be a max. You also should realize a multiplier, this is essentially a constant. The slope of this is constant. So you got a constant that's increasing as the line goes up. So that means there's not going to be any wiggles like that. There'll be one turnaround point, and that's when this graph takes over from that graph. And the only reason it takes a while for this to take over from that is because we've got a million multiplier here. Okay, so we're going to look at the max of this. So the derivative of this says we can just take the multiplier out front and find the derivative of the internal. And the derivative of the internal says I can ignore that 1 and just find the derivative of this. It's just so long as I remember to multiply it all for that. Okay, this is the product function, so I have to take the derivative of this times this plus the derivative of this times this function. Fortunately, the derivative of this is just 1, and the derivative of this turns this plus sign into a negative 0.001 times that, because the derivative of this is the same as the function times the derivative of what's up here times this as a function. So far, that's what we have. And I should have kept the profit around. And don't forget the whole thing is being multiplied by 10 to the 6. So this was originally 1 plus. So it's the original equation where 10 multiplies that whole thing. Okay, I can see that I can factor out this from both. It's going to be times x minus 1, so I'll just factor it out first. So when I factor that out from both, I get 10 to the 6 up front times that. 1 minus 0.001 times x to the minus 1. Great. Now, quite quickly, it's obvious that this can never become 0, so I can just ignore it. But the bracket can. So when I solve it, I get 1 minus 0.001x plus 0.001. That becomes 1.001 minus 0.001x. Just multiply. When does that equal 0 is the question. We can just multiply everything by 1,000. So you still get 0 on the right side. Over here you get 1,001 minus x, 1, 2, 3, is equal to 0. So it's when x is equal to 1,001. I think, if I did the calculations right. If I didn't do the calculations right, that process is correct. You've got to take the quotient rule. It's easy if you keep the 10 out of 6 out of there, and you'll discover once you factor out the e value, it's whatever's inside the bracket set to 0 is what's going to give you your max. Let's just use the Desmos at this stage. Okay. So because we're dealing in the 10s to the 6s, let's just get rid of that. And then just multiply it by that after. So yeah, there's my x value that I wanted. So if I was going to find my y value, I would do this. I would do 1,001, comma, 10 to the 6, 10 to the power 6, times my f of 1,001 to correct for it. Label. So it's actually way, you'd have to change the y's for steps of, oh, I guess 10 to the power 6. Put the 10 power to the power 6 back in and see if we can just see it. There it is. So indeed, that is the max, so we did get the right x. And you can also see from at 500, it's on its way up. So at 500, that's the max at 500. Since there's only one max, that's the conclusion you can reach. You can say, okay, well, there's only one max. Since it climbs to that on the left, it's going to be 500 on the left. It's going to be the max. So at 2,000 items, the max is when you sell 1,001 items. And at 500 items, the max is when you sell 500 items because there's only one max. And at 500, it's still on the way up. Make sense? Okay, suppose the monthly revenue is dictated this, where the maximum capacity is 800 units. Determine the number of units to produce in order to maximize revenue. So again, it's taking the derivative and setting to 0. And this time, you're going to discover there might be two possible answers because this time we're dealing with an x squared. So that 30, it helps to determine, and I think they said maximum is 400 units. 800 units. Okay, so if you look at it, plus 30, when this is 0, this is 0, this is 1, this is 0, so that's the units sold at 0.30. So we're probably dealing with a weird, huge exponential growth that eventually then comes back to 0. We have to use the product rule here, which means I'm going to take the derivative of that times this function, and I'm going to add the derivative of this times this function, and we're going to end up with an x squared. So I think you're going to have a max and a min here. You're going to have something weird like this. And they're only concerned with this part, so it's safe to say that the second x value will be your max. So the derivative of this is 80x. And the derivative of this will make this number minus, like that, times 40x squared. It's clear, and since it's a big old minus between them now, like to see it better like that, it's clear I can factor out this, and I believe I can factor out a 40x. So I can take 40x out and the e. Out front. And when I do that, the first bracket, when I factor out 40x here, I got 2 minus 0.4. This is gone. When I take 40x out, I'm left with that. Oh, it's not too bad. So when I set it to 0, again, it's clear this growth curve can never hit 0. Although, technically, yeah, right there, when x is 0. So there is one value. So that means there's a weird, probably bounces down at 0, 0, then comes up, which will explain that there. And then when I set this to 0, if I multiply both by 10, I get 4 at 20 minus 4x. So you get 20 is equal to 4x. So it's clear when x is equal to 5, we will maximize the profits. When I plug in 5 here, 5 times this is minus 2. So it's 40 times 5 squared divided by e to the 2. So that should be the y. So it should be 5, comma, that, and the other min point will be 0, comma, 0. Let's graph it. I don't want to spend too much time on these. Yeah, just as suspected. And let's see, did I hit it? Yeah, we got it. Did I get the right y value though? No, I calculated the y wrong. So when this is 5 here, it does become -2, and this does become 5x squared. I think I just calculated it wrong. Oh, I forgot to add 30. There we go. So that's where I made my mistake. I forgot to add 30 afterwards. So there we go. Makes sense. Then it drops as the growth curve takes over. Here's the two curves separately. So you can see on the left side, they're both very high. So you get this extreme acceleration. Then when the parabola goes through 0, 0 here, because its vertex is 0, it creates a 0 in the black curve. So the parabola and, sorry, the red curve. The parabola and the red curve. Yeah, but it gets 30 gets added to it, so that's why it's up here at 30. And then as the growth curve takes over here, even though the parabola is shooting up, the parabola has power. The parabola affects the curve quite a bit until you hit the peak here, and then the growth curve takes over as a much stronger result, which is why eventually your growth curve and your main curve, but there's 30 difference because of this plus 30, will essentially start matching as the growth curve becomes so small that it negates the value of the parabola. And it's only up here at 30 because we've added 30, and it will always be slightly above 30 because this purple curve is always slightly above 0. Makes a lot of sense. Was that the overall question? I can't remember. I think they just wanted to know max and min. Yeah. A rumor spreads through a town, so. And they want to know the rumors represented by a percentage of people. The percentage of people is based on time. And again, we have a small decay curve subtracted by a main decay curve. As we saw last time, that produces a weird little bubble like that. So we're going to find a max, and this will be the x-axis somewhere. We're going to find a max somewhere there, just like the other subtraction, which was -3 to the t. What's the highest percent of people in the first 3 hours? Okay, where does this occur? So that means we have to take the derivative of this. Unfortunately, they're being added, so the derivative is quite easy to take. You can just take the 100 out, and you're going to take the derivative of this first one, which is just minus e to the negative t, and the derivative of the second one, which is just minus plus 4, because the minus 4 comes down, to the e minus 4t. You cannot take an e out of this because they don't have the same exponent. However, you can set it to 0. We quickly discovered the 100 is pointless. And when this goes to the other side, it becomes, when does 4e to the 4t equal to e to the negative t? If we take a ln of both sides, try to remember this plus 4 will matter. We take a ln of both sides, we have to use the product rule here. So you get ln of 4 plus ln of e to the minus 4t, and that's where a lot of people go along. And over here, ln of e to the minus t, you just bring the minus t down, times ln of e. Ln of e is just 1. So far so good. Now we need to bring this 4t down. Okay, if we bring it down in front, it goes like that. That's the rule of lns, and ln of e is 1. So you get this. Now I can add 4t to both sides. And you get ln 4 is equal to 3t. So when t is equal to ln 4 divided by 3, you'll find the time of max spread of rumor. Then you have to put it back in, which means what's the percentage? It's going to be 100 times e to the negative this minus e to the negative 4 times that. So it'd be good to keep that in my calculator. We'll just clear the memory just in case, and then we'll just add it again. There we go. And we're going to just multiply it by 100 afterwards, okay, because it's a percentage. So we're going to get e to the power of my memory is equal. Let's switch the memory. Let's clear this. Let's bring back the memory and make it negative, because all my memories are going to be negative anyway. So you get e to the power of memory. Let's try that again. Here's my memory. Switch it to negative. Clear my memory. And add that. There we go. So e to the power of my memory is that minus, open brackets just to be safe, e to the power of, open brackets just to be safe, 4, we don't have to make it negative because we made the memory negative, close brackets, and let's see, equals, times 100. So I believe 24.6% of the people, and there's a high probability that I made a calculation error, as you've seen of the complexities, and that's okay. You got the idea that I just plugged the time in. I'm more concerned that I got the time right. Okay, we got 100 times e to the negative x minus e to the negative 4x. Let's hit home button, see if it looks like get rid of this thing. And sure enough, it's going to hit a peak up here. And I got everything wrong. Let's make sure I got the equation right. Yeah, I got the first calculation wrong, which will make my second calculation wrong. So I'm more concerned about what I got wrong there. Oh, I actually did the division wrong. That's pathetic. Here's ln 4 divided by 3. So I had it correct. I just for some reason spat out the wrong number. Oh well. The process is correct. That's all that matters. This is actually the number that my calculator actually should have spit out. For some reason, I got this stupid thing. So there you go. ln 4 divided by 3 is the correct answer. Just for some reason, I got that. So, had I had the right thing, I could have plugged it into the equation and found out the max. 47% of the people have heard the rumor. My apologies on that calculation error. I don't know what happened. But it did produce the same graph. as before. Notice it's even sharper as this percentage here. See, this exponent was bigger than the earlier one, which was minus 3t. So this makes even bigger spikes, and we'll prove that by making it minus 5x, bigger spike. Make it minus 6x, bigger spike. Make it minus 7x, bigger spike. And the spike looks like it's going up consistently. It'd be interesting to see how the different spikes changed. So you just, and obviously if I make it smaller spike, we get a very small bump. What if I make it just slightly bigger than 1? We get an almost non-noticeable spike. There we go. We get a tiny bump, but still a bump. So it's worth noting that this will always create this kind of graph. I don't know why it's worth noting, but it is. This one's one of the most useless questions I've ever seen, except to say that the growth in the beginning compared to the growth at the end is astronomical. Like in the first year, they only make 15 million, and by this year, they make like 1 trillion. Compare the growth rate 1947 with the ending rate. So that's essentially just punching in time of 100 over here, and you'll see how significant it grows. And it might just be easier for me to put it in the graph, which is what I'm going to do. And there it is. So we're only concerned about the first 100 years. So we'll make that a little bit shorter on the y-axis. And we'll just make our y-axis not as crazy. There. Kind of get a good idea. But in the beginning here, so we're talking millions, there's 2.23 million, 53 million. Here we hit 100 million. Still in the hundreds of millions, 300 million, 400 million, 500, 700 million. Here we hit 1 billion. Then look what happens from like year 60 onwards. The growth is just ridiculous. Right there, the amount after 100 years, here I'll just put in 100, comma f of 100, and label it, and we'll put in 0, comma f of 0, and we'll label it. So you can see in the beginning you're making 1.5 times 10 to the 7, if I got that number right. Is it 10 to the 9? Yep. Which is $15 million. And by the end, you're making 10 to the 9. 10 to the 6 is a million. 10 to the 9 is a billion. So you're making $28 billion in 100 years. Let's look into the future and do 150, comma f of 150, and label it. So that means 50 years later, look how much more you make using this curve. You're making $1.2 trillion just 50 years later, and that's because the growth is ridiculous. This is a good example for young people saving, by the way. when you save early in the beginning, your money won't grow much, but near your aging years, your money will take off astronomically. That's the power of compound interest. As the interest gains interest, it's the same as a growth curve. Interest gaining interest on interest on interest on interest is the same as an exponential growth curve, just not as severe unless you get multiple assets earning interest for you. For instance, when you start getting employees and you get a piece of all their paychecks, you're making exponential growth the more employees you have. So this is an interesting graph, only in the growth of it. So from 1867, they discovered that you grew more an industrial economy rapidly if you achieve the objective of importing foreign capital and technology. India did this, by the way. What happens is you open factories and the country just uses your labor while you work for them, and they keep their technology secret. Interestingly enough, India said, we'll give you the labor, but you have to give us the technology. And then they started their own technologies, and their economy is technically, even though there's a lot of poverty in India, their economy boomed from that strategy. Very smart. Amount of U.S. investment increased, so you can see that the overall industrial economy skyrocketed with this. And then they say graph the curve, compare the growth rate from this to this, so from 1947 to 1967. So we have to do 47 is 80 years in. Get rid of the future here. So you can see that it's 6.2 times $1 billion. So $6 billion. And here it's $28 billion, which is a growth rate of about 4.5 times as much. So this is 4.5 times as much revenue as the 80. Okay, what was your question? I don't know why. I mean, it went from millions to billions, so it's 1,000 times the original starting investment in 1867. I'm not even sure how they answer that in the answer book. So they're saying tag on another 10 years and compare it to the actual investment. Then tag on to 2007. Okay, so 10 years is 110, and 2007 is 50 years later. I think we did that. Technically, I don't think this model actually worked the way it's shown. I think there's a maximum you hit, especially as the U.S. economy, if the U.S. economy flounders. You can see the vast difference. This would be 1977. They're making 5.9 billion, and here they're making 1.2 trillion. So vast growth in just 40 years. So again, this isn't really a derivative question, which is why I find it weird in the book. It's fascinating economically. So here we have a growth, very simple growth. So let's do this one. And that's why I didn't like number 7. I'm sorry I wasted so much time on it. Number 8. We have a simple growth. And it's a very simple formula. The bacteria is going to grow at a doubling rate. So they even show us the base is 2. Do a little analysis here. Ask yourself, normally it's 2 to the t, which means when t is 0, you get 1. When t is 1, you get 2. And when t is 2, you get 4. And when t is 3, you get 8. So it would double every year, right? How fast does it double in this thing? Well, look, we have to ask ourselves, when will this exponent here be 1? When will that exponent be 2 to the 1? Well, when t over 5 is equal to 1. Bring the 5 up when t is equal to 5. So when we do it on the actual thing, we put 5 over 5. Sure enough, that's 1. So that means that's the first time it doubles. So in year 0, it's 1 because t to the 0 is 1. And in year 5, we see it doubles. When will the next period of doubling be? Well, looks like it's going to be every 5 years. So when will this exponent reach 2? Well, when t to the 5 is equal to 2, bring the 5 up, 10. Sure enough, when I put 10 in here, 10 over 5 is 2. 2 to the 2 is 4. So in year 10, it doubles. It's quite obvious that every 5 years, these bacteria will double. And keep in mind the culture rate's given by that, where n is the number of bacteria, t is minutes. The colony is allowed to grow for 60 minutes. So it's 60 minutes here. 60 divided by 5 is 12. And 2 to the 12 is 4,000 bacteria. And you can see how fast it grows. Even though it's every 5 minutes doubling, even though it's doubling every 5 minutes, we can see that at 60 minutes, we get 4,096 bacteria. Even though it doesn't look like it down here, sure enough, 25 is 32, 30 is 64, 35 is 128, 40 is 256, 45 is 512, 50 is 1024, 55 is 2048, and sure enough 60 is 40,096 as calculated. So you can see that initial growth is small and then it skyrockets, and that's the nature of exponential growth, and that's the nature of disease spreading. It's why people with expertise understand the seriousness of this, and people without expertise will say it's not serious. But in reality, if you let a disease run away to the later stages, there's no way you can stop it. There's no way you can stop a rampant disease once you let it go too far. And it's the mistake the US made and Brazil made. You're essentially executing your population. And then by the time you believe you're experts, it's too late. Okay, let's get to the question at hand. Then they introduce a bacteria killer called an antibiotic. Kill the bacteria. The number of bacteria killed is given by this curve, e to the t over 3. Now it's quite clear now that this thing doubles every 3 minutes now. So this killer is growing every 3 minutes. It's also clear that this base is bigger than 2. E is 2.71. It's just a number, and it goes on and on and on and on. But it's bigger than 2. So not only is this antibiotic killing bacteria faster than the original rate, it has a bigger base. Determine the maximum number of bacteria present at the time when they introduce it. Well, that's 60. It's right there. And determine the time at which the bacteria will be obliterated. Well, since this is the curve that's killing them, and this is the amount of bacteria when that antibiotic is introduced, the bacterias, all these will be eliminated when this reaches that number. In other words, when the subtraction equals 0. Rearranging it's just as I said. If you add this to that side, when we add e t to the 3, we get that this will occur when e t to the 3 is equal to the bacteria when it was introduced. So when it can kill all of these with this growth curve is when the bacteria will reach 0. Well, we can take a ln of both sides. So you get a ln of 4096. And using our exponents, we can bring the t to the 3 down. That's our rule of logs, rule of lns. Ln e. Ln of e is 1. When I get t all alone, I get t is equal to 3 times the ln of 4096. So that's quite interesting that the T, this bacteria will kill off all those bacteria in 24 minutes, which makes sense. It took 60 minutes to grow that. This is a much faster rate. It's almost twice as fast. And this is a much bigger base, E, which is why it only took 24 minutes to obliterate them. And so we can quite easily see this. Here's our original bacteria growth. I like X because sometimes the thing gets confused. Here is our point at 60 minutes. There, that'll be easier. There it is. So that's when the bacteria kick off. Now, our other curve is equal to this. Is equal to that. Now, if I really want to see where it connects, I can just do x minus 496 to join them. Let's see, will that technically work? I'd have to do 1/3 times x minus, no, x minus 60 rather. There we go. To join them, so that I essentially start my decay curve here. So now I can get a total time. And you might say, oh, it's not clear to me. Fair enough. I'll just turn that off so I don't confuse you. And I'll just put in the actual curve. And the question is, when does that hit 0? And you can see that it hits 0. Oh, I got to get rid of the 60. You can see that it hits 0 exactly as, and I'll turn off the other one. It hits 0 exactly as we said it would, 24.95. By the way, when you want to figure out what that 0.95, that's not 95 seconds. 0.9532985 times 60. That's 57 seconds. So be aware that because we're working in base 10 and time is base 60, and even that 0.19 is 19th 100ths of a second. This up here is 0.9 is 95 100ths of 60 seconds, which is 57 seconds. So be aware, don't confuse your time with base 10. But you can see it gets obliterated. However, if I want to mark the start of this antibacteria with this, I just use my translation knowledge, and I simply move my curve over to the right 60 minutes by subtracting 60. Now ask yourself, what is 24 minutes, 24.9 plus the original 60? Well, the bacteria should now be obliterated at 84.95 minutes. And sure enough, it is. And that's an interesting way that this is called a timepiece, which you learned. And if we really wanted to be more specific, we would limit the range of this sort of like that. And we would limit the range of this, sorry, the domain of this, to that. And we would change the colors just to be less confusing. So the blue represents the growth of bacteria, and the red represents the introduction of the bacteria, which pretty much kills off their growth right away. And the combined gives us very clean answers. It's 24 minutes later, which is 84 minutes. So if I started the bacteria growth here and introduced the antibiotic, this would be the total time it takes to start and kill the bacteria. These actually do have practical applications in the real world. Explain the steps that you would use. Oh, Lorianne is studying two different. This question is incredibly badly written. Very, very badly written. And the problem is, when they introduce the total function at the end, you think you've got to figure out the derivative of that, which is ridiculously impossible. In reality, they're just asking you what's the max of this curve and what's the max of that curve. So it's clear that this one, if you look carefully and you see that 20, you've learned that, okay, time has to be 20 for this to become 1, which means her effectiveness on this one goes up every 20 hours, because it's in hours. And her effectiveness in this one goes up every 10 hours. And I know it's a decay curve, but it's also multiplying by the time both times. So essentially this one, the efficiency goes up faster. And this one, the efficiency goes up slower. So they're, as we know already, we have an increasing line multiplying a decay curve creates still these big spikes. So you're going to have one that spikes early and one that spikes later. And the way it's phrased is it's asking us to take the two derivatives, combine the two functions, and take the derivative, which is ridiculously complicated. In reality, they just want us to find the maximum of them individually. And on a scale of 1 to 10, so the E is going to come out as 0 to 10. It's based on time. You really just want to find the max of these curves. So the derivative of this one, fortunately, you just keep the multiplier separate. The derivative of the internal, the 9, doesn't even matter anymore. However, the reason this is complicated is this a product. So you get the derivative of t, which is 1, times the derivative of the other, times the function of the other, plus the derivative of this function, which turns this into negative 1 over 20, times, and then you've got to keep the main function, times t. Now, fortunately, I can take e to the minus 20 out of both of them, minus t over 20 out of both of them, and I'm left with 1 minus t over 20, because this t just comes over here, which is pretty easy, because when I set it to 0, I realize this growth curve can't equal 0, but I get 1 is t over 20 equal to 1 at t is equal to 20 hours. So for this one, it makes sense that there's some link over here to 20 hours, because this will become e to the 1, and that's the only time that maybe this growth curve maximizes. And then keep in mind that you've got to plug in the 20 back in here to figure out the y value. Okay? So when I do that, assuming my calculations were right, I get 0.6 times 9 plus 20 over e to the 1. Okay? 20 divided by e plus 9 times 0.6. So I'm going to get a y value at here. So she's going to hit an efficacy rating of 9.8 at that time. What about the other one? Well, it's the same sort of thing, except the multiplier is different. The derivative is, we can just keep this out front. The 10 doesn't matter. However, the equation will later. And we take the derivative of that. Fortunately, it's the same thing. Get e minus t over 10 this time, plus, becomes a minus when that comes down, times e to the minus t over 10 times t. So this t essentially just goes over here. When I take e to the minus 10 out of both of those, I get 1 minus t over 10. When I set that to 0, I quickly realize this can never be 0 because it's a decay curve now. But the other thing can be. And all I did was take the derivative and set it to 0. So when is 1 equal to t over 10? When t is 10. Then you got to plug it back in. So now for the second one, we know maximum efficiency occurs at 10. And then we plug it back into the main equation, which is this, to figure out what that efficiency rating was. So we get 0.5, which times this is 5 if you want. 5 plus 0.5 times 10, which is the t, so 5, over e to 10 over 10, which is just e. So 5 divided by e plus 5. The efficiency rating then is only 6.3, assuming I did it right. The max efficiency she can achieve on this one occurs at 10, and it's that. And the max efficiency on the one occurs at 20, and it's that. Let's see if I got it right or if I got it wrong. We're going to do the first one. So I'm going to use x. Okay. It's very hard to see it. Let me make sure I got the multipliers right. 0.69 plus t plus x times e to the negative x over 20. Yep. Let me just squeeze the x-axis to x to 30. Okay, and we're going to squeeze the y-axis to 0 to 10. There we go. So it's quite clear that the max achieved is right there at the 20 hours, and indeed the maximum efficiency is 9.615. And then this other one we'll call g to the x is 0.5 times 10, and that. And it's quite clear that that maximum efficiency occurs at this, at 10 hours. And just to be sure, you can set your derivative of f of x to equal to 0, and it should cross. Sure enough, it's saying 20. And you can also verify that your f of x is 20, comma, f of 20. And you can label it, and the other one you can label as 10, comma, g of 10, and you can label it. And did we get the points, the 6.8 correct? We did, right there. And it's surprising that the max efficiency can be a 6.8 out of 10. Finding the combined derivative of these things, if you actually make a new function and call it f of x plus g of x, finding the max efficiency of both of them requires graphing, because you're talking about a quotient that's so complex. So you'd think it's just the average between 20 and 10, but it's not. It's a weighted average because one gives you a higher efficiency than the other. I imagine it might be possible to take 20 times 9.8 plus 10 times 6.8 and find a weighted average there. I don't think that might work, but I doubt it. So 20 times 9.815 plus 10 times 6.839 equals divided by 2, and then actually you'd have to then divide it by the average of their efficiency. I think you'd have to divide it by like 16.6 or something. It's quite complicated, and even then I didn't get it. So because these efficiencies are weighted differently, it pulls time one way or the other, because this one's much higher efficiency. The average total efficiency ends up being 15.69, but taking the derivative of these two things added together, I mean, okay, maybe I can do it. Like, maybe I could. No, because once you separate them, you'd end up with this. Very complicated. And I wish I'd kept the derivatives around. You'd have to add their derivatives, and I believe it was 0.6. Oh, I can't even remember the derivative. But it had e to the minus t out of over 20 out here, and it had 1. Did it have 1 minus t over 20? And then you'd have to add the other one. And because they're not the same exponents, I think it was like that, wasn't it? But there was a multiplier out here too, wasn't it? It was a 0.6 times this one, and a 0.5 times this one. When you set it to equal to 0, you'd have to set one equal to the negative of the other. Then you'd have to divide your e's out. It's just nightmarish. It's not as simple as setting that to 0. You'd have to find a way to factor out e's, and that means dividing them. I mean, you could try doing it this way. So this is 0.5, I think it was. So that means this is equal to negative 0.5. You could try dividing e to the negative 10 over t on both sides. And then you this would be a subtraction, so it's minus a minus, so it's plus. So you get plus t over 10, which is 2t over 20. So you end up with plus t over 20 over here, and you get rid of your e's. I mean, theoretically, that's fine. You now have negative 0.5 on this side. What could you do now? You can't subtract them. It still is nightmarish because you have to find a way to get rid of the plus. I suppose you could divide it now by 1 over t over 20 on minus t over 20 this side, and you get 1 minus t over 20 on this side, and you can see where the weighted thing comes in now. And you could also divide it by this, so you get 0.6, so you get a minus 0.5 times that over that has to equal e to the t over 20. Then to solve this, you'd have to take a ln. Wow. I would suggest instead distributing this. And then you notice you're going to get a ln t over here. Well, actually, maybe we're almost there. Minus 0.5 plus 0.5t over 10 over 0.6. Yeah, the problem is the bottom has two factors here. 6t over 20. If it was possible to break this down into single fractions, it would work. But you're going to have this in a denominator of 1 and this in the denominator. That's just hell. And you got to take a ln of it. Then you somehow got to get t isolated from that ln, so you get a product. So you're going to get ln of 0.5 plus ln of t. Over here you're going to get t over 20. And how do you get the ln of t without a t? It's just nightmarish. Very complicated. That's when the graphing takes over and you discovered this weighted result here. When I first read the question, I thought they were asking us to do that, and it would take an hour or more to do it by my hand. Okay, explain the steps. We're going to do 10 and 11, and these are actually easier. I don't know why they're later in the questions. They're actually easier. Let's focus on this one. Between -2 and 2, all right? What's going on with this? You got a line. It's subtracting a growth curve. So in the beginning, the negative is going to stay a little bit more negative, not too much. And then when it crosses through 0, 0, that's when, by the way, x is 0, this is 1. So you get 0 minus 1. So it's going to cross through. When x is 0, we get 0 here minus 1. So it's going to go through here at 0 comma minus 1. And over here, you essentially got a growth curve that also goes through 0 comma 1 and 1 comma e squared. Okay. Here you've got a line in blue that just goes through there. When you're subtracting this part, this minus this small positive, you're getting this slightly below line. But over here, as this exceeds that, you're going to get a big dive. And so you will should see a huge dive as this growth curve takes over and the negative numbers far exceed the line curve and send it into a negative. But right here in the beginning, when you get 0 minus 1, it sends it down here. And the line curve, when x is 1, you get minus e to the 2. So actually, no, it'll probably dive at the 0 comma 1. So you're going to get, the best thing to do is to take several points, right? So we can see when x is, let's start with the extreme. When x is minus 2, you're going to a e to the minus 2 times 2, which is minus 4, which is the same as minus 2 minus 1 over e to the 4. So it's a very small number. And you could plot it. And see, it only reduced the minus 2 by a tiny bit, which means we have here minus 2 comma as one of the points. When x is minus 1, we get minus 1 minus e to the negative 2, which is minus 1 over e squared. So we're also going to get a very small number. Which is almost the same as, and you just make a table really. So you're going to get minus 1 this. You're going to get minus 2 this. You can see on the left side of the graph, it's barely, the line is barely going to be affected. So you're going to pretty much see the line on the left side. And then of course at 0, we've determined 0 comma minus 1. And then at 1, you get 1 minus e squared. So you're just going to immediately see a dive. So putting it in order, this would be it, and this would be it. And then at 1, you're going to get 1 minus e squared. E squared is obviously like 6 or something. Oh, 7.8. So you're going to get minus 6 point. So boom, it dives. And then at 2, you're going to get an exponential growth of that. It's going to e1 minus e to the 4. Boom, look how much it dives. And that's because the growth curve takes over. So on the left side, you're going to see pretty much, if we were to graph this, you're going to see a line pretty much that starts to bend around here. It's going to hit 0,1 and then it's going to dive like crazy. And it's actually going to dive like that. So you're going to see what's essentially a decay curve on the right and a line on the left. Right to when it hits the x-axis, I think. And I believe the y-axis is going to be the highest point. The next step to drawing the curve is to take the derivative of these. So you get 1. What's the derivative of this? It's minus 2e to the negative 2x. You set that to 0, or to the positive 2x rather. This 2 came down, became negative. It didn't become negative, stayed negative. So you get when is 1 equal to 2 to the e to the 2x, or when is e to the 2x equal to a half. You take a ln of both sides. I'm just going to move it over here. This is just to find the max point. And you want to keep all the figures you figured out here, by the way. So we'll just put these over here. And then you take a ln of both sides. So you're essentially going to get 1 is 2x equal to the ln of a half. And it's when x is equal to a ln of a half divided by 2. You should be able to do that by now. I essentially took a ln of this side, brought the 2x down, the ln of e became 1, so I was left with 2x, and this is just the ln of a half. So what is a ln of a half divided by 2? So we discover a peak when x is this. And we should figure it out. So we're going to take that. We're going to add it to our memory, just in case we lose it. And we're going to subtract e to the exponent, open brackets, of 2 times our memory, close brackets, equals. And that's going to be our y. Now, that's weird to me, because the we've already figured out it goes through 0 minus 1. Oh no, it's not weird to me. It goes through 0 minus 1. This point is slightly above, right there. So we're going to see a line. We're going to see a straight line that maxes out here and then just dives. And that's how you graph it. It's much easier to just take values on the extreme points. And sure enough, that's exactly what we see. The left side is a line that's pretty much unaffected, especially as we get down here. And then as we get close, we see that max point that we just determined. Look at that. We got it exactly. We even saw the y-axis, and then we see this massive decline. And we can even see what f of 2 is indeed minus 52.59. Very easy to map using old school techniques and quite easy to understand what's going on once you start just doing an XY, because the interval's so small and the graph is so simple, it's possible to determine the intervals of increase and decrease. So that would mean when is the slope positive and when is the slope negative. So what you would do then for the second one is, what they're asking is, when is the derivative above 0? So to figure that out, you just find the 0 and figure out left and right. And then when is the derivative below 0? And it's the same technique. To do that, and I'm going to have to stop after this one. To do that, this is the product rule. The derivative of this is 2x times the function of this plus the function of that times the derivative of that, which is just that. We can take the e to the x out. We can actually take x, e to the x out, and we're left here with 2 plus x. We set that to 0. We can see quickly that when x is 0, we have a max min, and when x is minus 2, we have a max-min. So we're just not sure what. Now the easiest thing to do is to plug those max-mins in. So clearly when x is 0, we get 0. And when x is minus 2, we get 4 over e squared. How did I figure that out? I put it minus 2 here. Minus 2 squared is 4. Put a minus 2 here, which is e to the minus 2, which is the same as 4 over e squared. So I'm just going to take 4 and divide it by e squared. And I get this. So my points are going to be now the question just becomes which is a max and which is a min. One of these is, they both could be maxes, could do that and then that. Who knows? I don't think so. I think it's going to do something like that. So the simple point is the graph is either going down or up at 0, 0. Since we have an equation, or we did have a working equation of, I think it was x e to the x times 2 minus x. Was that it? Or 2 plus x? I think it was 2 plus x, 2x, x squared, took an x out, took the ex out. I think that's it. Since we have that as a derivative, we can just figure out what's going on between the 0 and the next point. So somewhere over here at minus 2 is something else happening. If we can figure out the slope between these two, we get all the information we need. So that's the question, is what happens at minus 1 in terms of the slope? So we put it over here. Is it negative or positive? Well, we get minus 1 times e to the minus 1, which is just minus 1 over a positive number, times 2 plus minus 1, which becomes 1. 1 times a minus. So that means the slope between this two, between minus 2 and 0, 0, is a negative slope, which means it's going down. The question is, on the right, is it going up again? So now we have to look at 1. What happens when it's 1? Well, it's clear when it's 1, we get a positive number, positive number, positive number. So the slope after 0, 0 is positive. So it's going up. What about to the left of minus 2? Well, we get negative number, positive number, and negative number. Huh, interesting. Because minus 3, which is to the left of minus 2, will produce a negative number in here. So we get a negative times a negative. So the slope is positive. So that means at minus 2, comma, whatever it is, 0.54, on the left side, we have a negative, right? In between them, we have a negative. Interesting. Let's make sure that. Oh, no, wait. On the right side, we have a positive. On the left side, we have a negative and then a positive. So that's what we have going on here, which means that 0, 0 is the negative and 2, 0.5 is the positive. Let's make sure that x squared times ex. And is that it? Is that what we have? Yes. So what did I describe? Did I describe it right? Where was my drawing? So I determined that on the left side, oh, right here, I have a bump up and then down. Great, got it. This is that, that's that. So sure enough, there's my min, and sure enough, there's my max. Now, it's much easier to take that than to take the second derivative, and that's because the second derivative of this will involve the product rule twice, because there's an x in here. Now, you could leave it in unexpanded form, and you still have to do the product rule twice. It's much easier to take the slope just to the left and to the right of the points, because the slope equation is so easy. So, the intervals of increase are, if I redraw it, it maxes here, goes down, comes up. So the intervals of increase are from 0 when x is bigger or equal to 0, and when x is smaller or equal, no, not equal, just bigger than 0, and x is smaller than minus 2. And the increase is between here and there. So increase, it's between minus 2 is smaller than x is smaller than 0. So this is the only spot where it's decreasing. And these two spots here, infinity, negative infinity, all the way up to minus 2, which is that. And from this point, 0 all the way up to positive infinity, which is that. So red's the moment the intervals of increase, and blue's the intervals of increase. And what's the absolute minimum? We've determined it's 0, 0. Very easy to take the first derivative. Taking the second derivative to figure out if the first derivative is max or min is kind of a waste of time. You want to do the old school left and right because the intervals are so easy. Okay, here's the graph of the derivative. You can see that where it crosses the x-axis is where the max and mins occur. And this here should be the inflection point of when this changes directions. And it does. There you go. So I'm going to call it quits because after this, there is a minor, very easy max-min points, very similar. Profit function. This is a distance that obviously as you go further, it's a line, but then it comes back from this, what is essentially a decay curve. And then you never reach home, it looks like. This is what we discussed with Lorraine. And this is an animal population one. So these ones here are quite easy. This one we discussed, and this one I'll probably skip because it's a conceptual question. But I will do 12, 13, and 14. Just not right now.